All right, the good news about Chapter 8 is that most of this you have heard of, but there are a few new topics, so just pay close attention and I'll try to highlight the things that you haven't seen before. This is all about bonding, which means two atoms can come together and form a compound. And the reason that they do this is to achieve the lowest possible energy. So they're trying to become stable, that's the key word there. So if they're more stable at a lower energy together, then they're going to bond together. If not, then they'll stay separated. So let's just go through the different types. For ionic, notice that electrons are transferred from one element to another. Metals are the ones that usually lose the electrons, nonmetals gain them, and when you get those opposite charges, the opposite charge is the fancy way to say that is an electrostatic force of attraction. So electrostatic means it has those charges. Keep in mind it doesn't have to just be a metal and a nonmetal. If you have something like ammonium, which is a polyatomic ion, notice that all of that is nonmetals. We have hydrogen and nitrogen. We can bond that to nitrate, which is another polyatomic ion, and that compound is still ionic even though there's no metal involved there. So really it just means that you have two ions. A lot of times it's a metal or a nonmetal, but it doesn't have to be. The smallest unit for this is called a formula unit, and remember that's not an independent unit, so when we talk about table salt and we label it as NaCl, it doesn't mean that you just have one Na and one Cl floating around as a partnership. What that means is that in this big crystal that you have of sodium, or sodium chloride, you have all these atoms. The ratio between these is a 1-to-1 ratio. So we write it as NaCl, even though it's actually a big crystal, and it's just that ratio between them. All right, if you're kind of zoning out right now, this is important. Coulomb's law can be used to describe so many things in chemistry, and we're going to come back to this law over and over again throughout the year. So this is a good time to go ahead and get it in your head what it is. The good news is you probably won't even calculate with it. You very rarely see any questions that ask you about that equation where you have to plug it in. What you have to understand are the concepts. So there are two different letters here that you want to focus on. This is talking about the energy between two ions. And basically what that means is the bond between them. So it's talking about the strength of the ion attraction. And there are two things that are going to affect that. One is Q1 and Q2, which are the numerical ion charges. So for example, Mg has a 2+ charge when it loses its valence electrons. Sodium has a 1+ charge. Those are the Q values, is these charges right here. So what this is showing is that the bigger the charges, the tighter the attraction is going to be, or the stronger the bond energy is going to be. So for example, if you have Mg, which is +2, and oxygen, which is -2, magnesium oxide, we have +2 and -2, that's going to be a stronger attraction than if you had sodium and chlorine, because those are only +1 and -1. So it's directly related to the value of the charge, the numbers. The second thing we want to highlight is the distance between the ion centers, which basically means the size of the atom. So if you have a huge atom attracted to another huge atom, that attraction is going to be not as strong as if you have two small atoms. So the distance between them is really just talking about the size of the atom. And notice that since it's on the bottom of the fraction, the bigger the atoms, the weaker the attraction is going to be. So most of the time what I've seen in AP chemistry is that they'll give you an example and say, why are these two atoms forming a stronger attraction than these two atoms? And so the two things that you want to look at are the magnitude of the charges. See if maybe one has a +2 and -2, whereas another one is +1, -1. And if they're all the same charge, then you want to look at the distance between the atoms and see if you have some really big atoms versus some really small atoms. All right, the next thing is covalent bonds, which this time we're talking about sharing. Whoops, oh, there we go. Sharing doesn't have to be, not a very good line. Sharing doesn't have to be equal. So nonpolar means that you are sharing evenly. Polar means that one atom is pulling a little bit harder, and so you end up with slight charges. And the way we show a slight charge is with a lowercase delta, which is like a fancy lowercase d. That just means a slight positive or a slight negative. So it just means that the charge distribution is kind of lopsided instead of having a complete positive and a complete negative. The smallest unit for this is a molecule, and this is different from a formula unit because it does exist independently. So when we talk about water, we are talking about a little family of 3 atoms that are floating around together as a unit. Bond length is going to be the best distance where you get the lowest possible energy. So if we have 2 atoms We have all kinds of forces of attraction going on here and repulsion. So we have the attraction of this positive nucleus with this electron, but we also have this positive with this electron, we have this positive with this electron, and this one with this electron. So the opposites are all attracted. We also have some repulsion going on between this nucleus and between this electron and this electron. So there's all kinds of forces of attraction and repulsion happening, and what the atoms are going to do is align themselves so that they're at the perfect distance where they have the minimum amount of energy. And energy is given off if a bond is formed. So remember, forming gives off energy, forming is exothermic, and breaking bonds is endothermic. So if they do form that attraction, it's going to release the energy, because now that they're at a lower energy, they have to do something with that extra energy, and they're going to give it off. So that's usually an exothermic process. Keep in mind that the type of bond is dependent on the difference in electronegativity. We've talked about this before. In fact, you did this part of this with your lab. So the bigger the difference, the stronger the attraction is going to be. So for ionic bonds, they have an extremely different electronegativity, and so we just consider it to be transferred. So if this one is super electronegative and this one is not very electronegative, we just consider it to be transferred, so it's 100% on this atom. If it's polar covalent, we might have one that's a little bit more electronegative than the other. So it's going to be like maybe 80-20. So it'll stay on one 80% and the other is 20%. So we do say that they're sharing because it goes to the other one as well, but it's not sharing evenly. So this is polar covalent. And then if they're about the same in terms of electronegativity, then it's going to be a 50-50 relationship. And that's where we call it nonpolar covalent. The electronegativity trend increases across a period because as you go across the period, you increase the effective nuclear charge. And that's a fancy way to say that you add protons. And the more protons you have, the more they can suck in the electrons, which shrinks the atom. So it gets smaller as you go across. And as it gets smaller and as you have more protons, it's going to attract electrons better. So that's going to increase the electronegativity. As you go, let's see, this says decreases within a family. I think they mean going down. So as you go down on the periodic table, they get bigger and bigger. And so it's harder to attract electrons because the electrons are sticking to the atom farther from the nucleus. So if we compare this one versus this one, the electron is going to stick easier to a smaller atom because it's closer to the nucleus. So the bigger atom has more shielding. All right, polarity is the difference in the two atoms' electronegativities. If they're not quite the same, then one can pull the electrons a little bit harder, so you get kind of a lopsided distribution of electrons, and that makes it have what we call a dipole moment, which is just a fancy way to say that you're going to get that polarity. There's a couple of different ways to show it. You can show it with the partial charges like right here. Sometimes they do an arrow like this one where you have the plus sign on the one that's more positive, and then they draw the arrow towards the one that's attracting electrons better. These are some examples. Let me just show you an example of carbon dioxide. So if you just focus on the CO bond, oxygen is more electronegative, so it's pulling harder on the electrons. But since you also have an electron on the other side, it's pulling just as hard. And so even though each bond is polar, the whole molecule itself is nonpolar because the charge gets distributed evenly. And it's a really great way to say that on the AP exam instead of saying lopsided or something. What you want to talk about is the distribution of charge. If it's evenly distributed, then it's going to be nonpolar. And if it's not evenly distributed, that's going to be polar. And there's a table on page 360 that can help you with that. All right, for electron configurations, just keep in mind that noble gases are already stable. They reach the octet rule. So for ionic bonds, they're trying to do that, and they're doing the same thing for a covalent. So bottom line is that they're all trying to become more stable, and they're stable, most of them, with 8 valence electrons. So they will either share or donate electrons, valence electrons, until they reach that magic number. You guys are good at doing this. This is just talking about crossing charges. So the main thing with ionic compounds is that the net charge, net means the overall charge, has to be 0 if there is no charge on it. So for example, down here, the aluminum oxide, the reason it's 2:3 ratio is to make the whole thing add up to 0. Aluminum is +3 times 2 gives you 6. Oxygen is -2 times 3 gives you -6. And so the whole charge is going to be 0. But we've already gone over some of this. All right, and the last thing for this video is just the sizes of the atoms. First of all, anions means it's negative, cations means it's positive. Remember, look for that lowercase t means plus sign. So the more electrons you have, the more repulsion you have among the electrons, and so the more the atom kind of spreads out, all the electrons move away from each other, and it makes the atom grow. And so the more electrons you add to an atom, the bigger the radius is going to get. But it's the opposite for cations. So for cations, if you lose electrons, then the remaining electrons don't have as much repulsion, so they can get a little bit closer to the nucleus, and so that shrinks the atom. And if you ever see this phrase right here, the prefix iso means same, just like isosceles triangle you probably learned about in geometry. So isoelectronic ions are ions that have the same number of electrons. And if they do have the same number of electrons, then what you want to compare, if you're looking at the size of the atom, you want to compare the nuclear charge, which is the fancy way to say the protons. So if you have two atoms that have the same number of electrons but different numbers of protons, the more protons you have, the smaller the atom is going to be. And we have one more section for today, but it's going to take me a few minutes to explain it, so I'll do section 8.5 in another video.